Sam has figured out what I'm doing before class. I've been waiting for class to start. That is true. It's part of my very exciting existence. But anyway.
You live in your office, right?
Live in my office?
No, we don't.
Thankfully, no.
Spider-Man doesn't allow you to do that.
Although I would like to get a cot for my office. That would be nice. I used to have one in my office as a grad student.
You should get like a hammock.
A hammock? I don't know. I used to sleep. I used to have like an easy chair in my office I'd sleep in, which was pretty nice as a graduate student. One of my regrets is not living in my office as a graduate student. I would have saved so much money. I know it's illegal, but I'd be like $10,000 ahead.
Why is it illegal?
Why? You know, that's a good question. Why is it illegal? That is a really good question.
Fire codes, you have to have a window in a bedroom. And so
Codes, inspectors. I feel like if I was a framer of the Constitution, these things we're talking about right now, they would offend me. Right. I will begin. Dear Father, we thank you for this day. Thank you for the students. We thank you for the break that's about to start. Just guide our work today. Help us to glorify you, what we do, Lord. In your name I pray. Amen. Okie doke. So I am hoping to wrap up the bulk of my comments about Chapter 6 today, actually. So let me, but I figured out that the way he's proving things, the way I was proving things at the end of last class, is not wrong, but it's also very implicit in the sense that we're defining the adjoint in a very sort of like, it's this thing that satisfies this equation, which is nice and everything, but I'd like to show you sort of a more direct calculational approach, which is not in the Inzel, Spence, and Freeburg. And personally, I need to introduce the dual space and start working with the dual basis to do this in the way I want to. So let me just go ahead and do that. So I told you before about the, we're going to let V be finite dimensional vector space with inner product this over F. Now, admittedly, I don't really need the inner product or the finite dimensionality to define the dual space, all right? But most of the theorems I'm doing today concern finite dimensional vector space, inner product space. So I told you guys before, although I haven't, and so here's the definition. V with a star on it is called V dual. This is basically just the set of functions from V to the field such that F is linear. In other words, V dual is really just the linear transformations from V to the field. A dual vector is like this. F is a dual vector, aka a linear functional. Now, these are most exciting if you deal with the infinite dimensional case, but since this isn't a course in functional analysis, we won't be doing that. But the dual space is very useful. Let me show you how. So, fundamental theorem, definition. If beta v1, v2, vn is basis for v, all right, then beta with a star, upper star on it, is the so-called dual basis. The so-called dual basis to the basis. And what this thing has in it is v upper 1, v upper 2, v upper n is the typical notation, where v upper I are linear transformations from V to the field defined by extending Vi acting on Vj equals to Kronecker delta Ij linearly. So the dual basis is a set of functions on the vector space, and they work in a very precise way. They give you back 0 unless they eat the vector which is the same as their index. So like v1, v1 is 1, but v1, v anything else is 0. All right? That's the way these work. And you can prove that that's in fact a dual basis for v dual. There's a theorem, which is this: if y is an element of v, all right, then y is equal to the sum I equals 1 to n of v upper I of y times v lower I. Let me put this theorem into words for you. This theorem says that we can use v upper I to select the ith component of a vector. Of course, the ith component with respect to beta, right? Let me prove that theorem for you. It doesn't take long. All right, so if beta is a basis and we pick y and v, what does that mean? There exist constants, right? C1, C2, Cn in the field, such that what? Such that y is equal to the sum I equals 1 to n of Ci Vi, right? Because we're assuming we have a basis beta with v1 through vn. All right? So what do? I just take this basis expansion and I act on it by my jth dual basis vector. So let us calculate v upper j on y. What's that equal to? Well, that's v upper j on the sum I equals 1 to n of Ci Vi. Now, I defined the dual basis by its action on the original basis extending linearly. You had a homework problem earlier in the course where you proved that's a well-defined thing, to extend linearly like that. It gives us a unique linear transformation. So anyway, using that linear extension here again, we pull out the sum, we pull out the constant, and then we've got Vj acting on Vi. No lecture at this point in the semester is complete without the Kronecker delta. So here it is, by definition, Kronecker delta Ij. As we have discussed, this is the natural enemy to the finite sum. And so we're just left with C sub j, which is what we set out to prove. See, because what that says is that I can take this, right, and I can take it and put it right back in here, right, which is precisely my claim in the theorem. Okay. Alrighty. So let's see here. Another theorem would be this, and this is really a corollary to a theorem we did before. But if we have a linear transformation T on V, all right, T beta beta, the ijth component of that, all right, well, that's just equal to V upper I acting on T of V lower j. Let me remind you what this is a corollary. So the proof of this basically is not very long. We previously showed, and here we're assuming that beta is orthonormal, all right? I want to assume beta is orthonormal All right. I will admit, some of the things I'm telling you are also true for just general bases, but we're mostly interested in orthonormal bases, so let me just tack that on at the moment. So we previously showed that the ijth component of the matrix of T was what in terms of inner products? Do you remember? We previously proved that that was T of Vj, comma Vi. That was the corollary on page 347 of Inzel, Spence, and Freeberg, which we went over in previous class. Now, so all you got to do, right, is what? Oh, we have another result too, which is what? Y is also equal to what? We could also do it in terms of inner products, right? What was the inner product version of this theorem? Let me do it beside. I really should make this point already. I'm sorry, guys. I should have made this point here. This is also equal to what we learned before. In terms of inner products, what was this? How do we select, assuming that beta is orthonormal? Let us agree. The basis beta is orthonormal through this lecture. Okay.
I was saying IPIs.
Oh, it's not you, I suspect. Let's see here. Let's see here. Wait, you saying what? Ivy. Okay. I don't know what's going on here. Okay, so this is what? Y? Vi. Remember? We can select the ith component. Oh, okay. I'm sorry. I'm an idiot. So my point here is to calculate, this is also what? I mean, so basically, I mean, a corollary to this theorem up here would be what? I can also state this, moreover, what we really have is that Vi of Y is equal to what? Right. So just to get to the point here and not run around, way around, this is just equal to what? This is equal to V upper I of T of Vj. Okay. So, what do we want? Let me just tell you our goal. Our goal is to define T star from V to V such that if we take T of x comma y, we get what? We get x comma T star of y. I mean, that's what we want. All right? So let me show you a definition then that will do that for us, definition. And I actually derived this using this dual basis stuff, but I guess the derivation you don't need to see necessarily. So T star of y, I'm going to define that as the sum I equals 1 to n of y, comma, T of vi, vi. Now this definition I give you is inferior to the book in one regard and superior to the book in another regard. It's inferior in the sense that it's coordinate based. My definition for the adjoint is using a coordinate system, the beta coordinates basis, the beta basis. So since I've defined something that's supposed to be independent of basis, right? to be careful, I have to actually show you that if we changed coordinates, if we used a different orthonormal basis, we'd still get the same adjoint. I'm going to have to prove that for you. But the advantage of my definition is I'm not saying, hey, T star is this thing that when you satisfy this equation, it's T star, right? This is an explicit definition. It gives you a way to calculate T star directly once you choose a basis, right? So that's nice. So we should check that this definition is, first of all, what? Linear? We need it to be linear, and we need it to satisfy this property up here for it to be consistent with what we looked at last time. So let's, first of all, can you see why it's linear? If I take C1y plus, CY1 plus Y2, what do we get? It's an inner product, so we have linearity there, right? We can pull the C out of the finite sum. We can break up the finite sum into two finite sums. And of course, that's C T star of Y1 plus T star of Y2. So there you go. My alleged adjoint is linear, at least, on V. Now we should check and see that it actually satisfies the condition we want it to on the inner product, right? That we can, it's related to T in that way. So we'll do that over here. Well, I'm probably going to regret erasing what I just erased. If I was smarter, I'd probably go over here since we already... Oh well. Live and learn. Let's see here. And I probably should put up here beta orthonormal just for the record. These are global comments. We also have that T from V to V is what? Linear. These things I'm assuming everywhere, but I sometimes forgot to write. All right. So let's calculate. I want to do T of x. Well, I should probably start with x comma T star y, right? My goal is to do what? In fact, if you think about this, if I can prove it on the basis, isn't that enough? Yeah, I'll tell you what, I'll be slightly less greedy. I'll do this for just Vj. If I can show that the identity holds for arbitrary Vj, then we can extend linearly because we have linearity in the first slot, right? So if I can prove it for Vj, then it extends for arbitrary x there. All right, so this is Vj, comma, the sum. By my definition, I equals 1 to n of what? What did I do? I can't remember. Y T of Vi. Vi, right? Now, the inner product is what? Conjugate linear, right? So if I pull this sum out, I can do that. But when I do that and I pull scalars out of here, like this is a scalar, what do I get? Complex conjugate, right? And then, oh look, wow, twice in one lecture. This is a very good lecture. Okay, so you know where we're going with that. Now, this flippity floppity, right? So this is T of Vi, comma y, right? And here you got your, I don't know if I'm, yeah, I guess I should, I guess I'll go ahead and, I'm not sure I need to do that. Okay. I'm not sure what's happening here. Oh, so then, so this is, I can pull that in here, basically, right? I feel like this is a longer version. So there I'm using linearity of the first slot. Multiplication on the right of a vector is understood to be left multiplication, right? I mean, we can multiply on the left or the right of a vector is our custom.
Why didn't you just eliminate the sum in that step and replace I, OK?
That's a good question. But any way you slice it, we get to t of vj here, right? Comma y, which then implies that x comma t of y is equal to, I'm sorry, t star of y is equal to t of x comma y for all x and y in V. All right. So that, of course, leaves a giant question, which is what? How do I know that my definition doesn't depend on coordinates, right? So it's useful at this point for me to define a term for you. Definition, and here I actually differ a little bit with Engel, Spence, and Friedberg. The definition they give in section 6.5 is not quite mine. They do admit that my what I'm about to write is equivalent to their definition in a theorem, but I think this is a better definition for us, so I'm going to stick with it. If we have, let's say, I don't want to use t, let's say, no, I'll say U is a linear transformation from V to V, where V is finite dimensional inner product space. All right. And U of x, U of y is equal to xy for all x and y in V, then U is said to be either one, if the field is the complexes, U is said to be unitary, right? And two, if the field is the reals, then U is orthogonal. Unitary transformation, of course. Sorry, words. Orthogonal transformation. These are the transformations which preserve the inner product. Right? These are pretty special linear transformations as they go, right? Like, can you think about this? Can you tell me anything? If I compared, for example, the length of x to the length of u of x, how would they be related? Proportionally, I will agree to that, but how proportionately? They would not be orthogonal. However, it is true that if x and y are orthogonal, then u of x and u of y would be orthogonal as well. Yeah. So these transformations preserve the length of vectors and also the angle between vectors as we define them. How do I know that? Well, how do we define the length of a vector? so u unitary, then the length of u of x is equal to the length of x. Proof. The length of u of x squared is the inner product of u of x with u of x, right? That was our definition of norm, in the square of the norm at least. But if u is unitary, that's xx, which is the norm of x squared.
So an orthogonal transformation is essentially just like a rotation.
Rotations would be included in orthogonal transformations, sure.
But there are more.
Yeah, there's also reflections,
Oh, right.
which I don't want to talk about carefully today, but I will tell you this much more. We have cosine of theta, right? What was it? It was the inner product of x and y divided by norm of x times the norm of y, right? Well, let me just talk about the proof for the real case, all right? The proof for the complex case is very analogous. So that's the angle between x and y, right? Right. The proof for the complex case is very similar. I'm adding to my proposition, and what? The angle between x and y is equal to the angle between u of x and u of y, if you'll allow me that silly notation. Would it be better if I did one of these? So how do you calculate the angle between u of x and u of y? Let's call it theta prime. We have the inner product of u of x, u of y, right? Divided by the magnitude of u of x, aka the norm of u of x, and the norm of u of y. Which, by the way, is what? The same thing, right? So cosine, that's a cosine, sorry. Cosine of theta prime is cosine of theta. Consequently, the angle is also preserved. So orthogonal transformations preserve the length of vectors, but they also preserve the angle between vectors, right? So the latter is known as, it makes them conformal. All right. So just want to introduce that terminology at the moment. We'll talk more about orthogonal transformations, especially what they look like for Rn or R3 in another day. Yeah.
Isn't that cosine theta equal to absolute value?
That would be if you'll just
Real case. Real case, so it could be negative.
In complex case, you take the absolute or
Yeah. Complex case, the same thing, but we have absolute value wrapping the inner product.
or take the real part depending on which angle you're talking about.
Yeah. Okay.
these two. I mean, the absolute value of it and the real part is different in complex case.
Yeah, but if I was doing the complex vector space viewed as a real vector space, this argument would apply to. I don't need a separate argument for that because that would be a real vector space and this is still good. Now, another property of an orthogonal transformation. Oh, why did I use this horrible thing? Yeah. Is the following. This is very nice. Another property of orthogonal unitary transformation. Well, unitary or orthogonal. Why do they have different names? I don't know. You could call both of them isometries, I suppose. Isometry. These are both isometries, linear isometries. Iso for same, metry mean measure. They have the same measure. Anyway, so proposition is that beta orthonormal and U a isometry. Then U of beta also orthonormal. So what I'm saying is that if you take an orthonormal basis and you look at its image with respect to an isometry, in other words, an orthogonal or a unitary transformation, then you get another orthonormal basis. The proof is really very simple. Here, U of Vj, U of Vi, U of Vj. This is shaping up to be the best lecture ever. Is Vi Vj, because U is a linear isometry, which by definition is invariant. The inner product's invariant, and of course that is Kronecker delta Ij, which goes to show you that that U of beta, which is, by the way, the set U of V1, U of Vn, is orthonormal. The Kronecker delta who lived? I guess you could say that if you wanted to. All right. Let me get to the point here. So, I'm not sure I want to get to the point here. Damn, man. It's actually kind of a pain to prove this thing is coordinate independent. All right. So let's suppose we have another coordinate system, gamma. All right. So suppose you have gamma W1 Wn orthonormal. All right. And suppose that we have that, to be specific here, Wi is equal to the sum over k of p ik vk. So what this means is that pik is the matrix of the linear is the components of the matrix of linear transformation, which maps the v basis to the w basis. So basically here, so what is the characteristic? I mean, if w is orthonormal, then we have wi wj is Kronecker delta ij, right? But that's also equal to the sum over k of pik vk, sum over L of P JL VL. And so we can pull the sum out. Sum over K, sum over L, we get PIK, P conjugate K, JL, and then VK, VL. So what this shows me is that the Kronecker delta Ij is equal to the sum. And see, I can kill one of the sums over there because that gives me a Kronecker delta KL. So I'll keep the K, sum over K of P I K conjugate of P J J K. All right? So what I'd like to do is to show you that if we change the coordinates on my adjoint, we get the same So what would curses, where'd the thing go? So here we go, t star y is the sum sum over I of y wi, right? Wi. This would be the formula for the adjoint using the other basis. My goal is to show you that that's the same as the definition that I gave you in the beta basis. So what I have to do is I have to take these w's and rewrite them as v's and show you that it doesn't make any difference. All right? So I told you how the w's and v's were related over here. Wi is the sum over a matrix pik vk. So I just do that here. And then this also, let's say the sum over L of P I L V L, right?
Isn't that supposed to be inner product of y and t of wi, or am I misunderstanding? On the top, on the
Oh, thank you. That would have been very confusing to me in about 3 minutes. Well, maybe 2 minutes. Let's see here. Yeah, there's supposed to be a t there, obviously. Thank you, thank you, thank you. Right, my definition. I'm trying to show that this definition's apparent dependence on the choice of basis beta is not really there. So yeah, I'm supposed to put a t here. All right. So using the linearity of t, I can do what? Using the linearity of t, I can rewrite this as the sum over k curses pik t of vk, right? And so that gives me sum over, and I can pull that one out too. So I've got a sum over I, k, l. I got my p conjugate, ik. I've got over from that one p I, l, right? And then I've got my y, I've got my t of vk, and I've got vl here. Aha, but what's this? Let's see, I've got them, let me write them. Let me just put that one first so we can see the pattern better. Schnikes. But good news. So what this says is that the identity matrix is equal to p conjugate transpose, actually. Because if you rewrite this, this is what? pik p transpose conjugate transpose kj, right? So this is actually, if we look at p star, right? The ijth components of that in terms of the matrix multiplication. So in other words, I is equal to p star, and by the way, that implies that p star p is also equal to I, which gives me, in fact, that this also is, yes, as you guys had anticipated. I feel like I have one too many sums here somehow. No. Oh, okay. So, actually, this is fine. But let me just rewrite it this way. This is the sum over I, the sum over k and l, cursor's still wrong. What's that?
Okay, and I'll have to read the same, because you're looking at the same WI. So, unless I don't know.
I mean, the I's match up because they're both from the WI. But the point was that this is sum over K and L, Kronecker delta, LK, which then gives me just one sum, which is all I need. So there we go. We're back to the formula for the adjoint in the beta basis. As you can see, the choice of basis doesn't matter. Now, he doesn't have to do that in Inzel, Spence, and Friedberg because he doesn't use a basis to define the adjoint. He just kind of says it's defined by this equation and works with that equation whenever he has to prove something about the adjoint, right? But this is nice if you actually have to calculate it. I've given you a procedure to calculate the adjoint, right? So there's that. All right, guys, so moving on here. Da-dum. Where'd that thing go? One theorem we have, which is pretty nice, is that the matrix of the adjoint with respect to an orthonormal basis is the adjoint. Well, I mean, here we're using star in two different ways, all right? The star on the right-hand side, this is conjugate transpose. So take the complex conjugate and transpose it, or vice versa. And on the other side, we have the adjoint. So let's see here. How do you get the ijth component of this thing? What did we learn? I have erased it. But if I recall correctly, we have that this is T star, right, of Vj, Vi, right? And so that is Vj, T of Vi, right? Nah. Well, I guess I'm. We have the opposite thing, don't we? I guess we don't know that yet, do we? I mean, we have that T of. The things we know, we know this, right? But I'm trying to pass the star over to here, right? What's that? Just do it. How about this? Instead, I erase the star and calculate Ji. Then I'd have a T here. I'd have an I here. And I'd have a J here. Then I can use the property that I already know, which is that I put a star when I move it over there. Right? And then this would give me the complex conjugate of T star Vj comma Vi, right? And that is what? This is the ijth component of the matrix of the adjoint. So you notice the ij and the ji, flippity-floppity. So that implies that the matrix of T with respect to the beta basis transpose is equal to the matrix of the adjoint with respect to the beta basis conjugated. And then take the transpose of that to get back up there. Now the other properties of the oh well, if I'd been smarter, I wouldn't have proved the coordinate independence for you. But, well, here we are. Let's see. So theorem 6.11 gives you the following properties for the adjoint. So here we have T and U linear transformations. Then we have the following properties. A, the sum of the adjoint of a sum is the sum of the adjoints. B, if you take a constant times the transformation, take the adjoint of that, it's the complex conjugate of C times the adjoint. C, if Isaac-Shoes is true for adjoints. D, and this one is the one that I wanted, but we didn't have yet. T, the adjoint of the adjoint is T again. And then E, the adjoint of the identity transformation is just the identity transformation again. So these are your properties of the adjoint. And one that's a little bit more exciting
So that should be ID, right?
Sure, if you like. Although it's also true, I mean, we can also define the adjoint of the matrix. So the adjoint of a matrix would be the adjoint of the linear transformation which the matrix induces. And so there's a list of similar properties for the adjoint of a matrix. The adjoint of a matrix is literally the conjugate transpose. So like the star notation is consistent. You notice this notion of star and that notion of star are quite different. This is matrix theoretic, whereas this was based on the interplay between inner products and the linear transformations, right? But they're consistent. So the lemma that we need here is that if T has an eigenvector, then so does its adjoint. So the proof is really nice. If we have T of V equals to lambda V for some V not equal to 0, then you can consider some vector Y in V. And if you look at, X in V, 0 is, of course, 0 with X, right? But we can rewrite that 0 also as T minus lambda times the identity acting on V, right? Now, so that gives me V comma T adjoint minus lambda complex conjugate identity acting on X. The reason I can do that is that the adjoint, I'm using the properties over here. The adjoint of the sum is the sum of the adjoints. When you take the adjoint of the complex lambda times the identity, you get lambda conjugate times the identity star, which is the identity, right, like that. And so what this says then is that if you look at the operator, t minus lambda bar times the identity, the range of this, right, the orthogonal complement to the range contains V, right? This V. But V, of course, is what? It's the range of t minus lambda bar id, right? Direct sum. The orthogonal complement to that, right? So what does that say? If this thing has V in it, what's that say about V? What's it say about this? It's not what? It's not all of? It's not all of V, right? So what's that say about the range of this linear transformation from V to V? Yeah, of course, yeah. Thank you. So this is not all of V, which says what? No, it says that t star minus lambda bar id has non-trivial kernel, which implies that there exists a w not equal to 0 such that t star w is equal to lambda bar w, which is to say that w is an eigenvector. I mean, if that, it doesn't have the whole, that means that there's something in there that's not in the range, which means there's something in there which is sent to 0. And that something is an eigenvector. So next time, guys, I'll define for you normal operators and self-adjoint operators, and I'll state the real spectral theorem. A little bit behind, so I'm going to cut some topic out of my planner. So you should be like, oh man, you should have posted another lecture instead, so that I won't miss any topics. But you don't want me to miss time with my family. Ah, very well played, well played. Anyway, guys, have a good break. My dream of finishing chapter 6